Okay, and my philosophy for lab instruction is to make this useful for your future career. So here I will be giving you sample code that you can copy and paste later in your career. So I've been hearing back from our more senior classmates saying that in their homework they're requiring coding. So I'm providing some sample code so that you can plot things as well as doing regressions. And in these sections, we'll also give you practice time for you to use the code and code it yourself. And in this lab, there will be two main sections. The first part will be quite boring because it's going over the basics of NumPy. And the second part will be more fun. It's basics of plotting. So please complete these surveys, and we'll get started with Python. Any questions before we start? Okay, so Python community is very vibrant because of its packages. It's not just Python doing its work, but also Python packages. And here I have listed a lot of packages that you might encounter in your future career, whether as a chemical engineer or doing data science manipulations. And these are the packages that people usually use. And to install packages, we need to use Python installation syntax. So the exclamation mark says that this cell will be executed in terminal command line. And the pip is a standard syntax, install umap, and umap is the package name. So usually you do pip install the package name. And you run it. I have it already installed. You can try it. It should be popping up a lot of instructions that's automatically installing the package. And to use those packages, it's not automatically imported. So you need to import those packages. The syntax for that is to use import. So for example, here you directly import NumPy, and you can use NumPy dot. Dot means that from NumPy package, you are using the version variable. So this is the NumPy version we're using. But usually people don't want to type out NumPy all the way. So people do import NumPy as. So this is called an alias. So this gives it a nickname. So you can just use np instead of NumPy. So this means that we're using the variable version from np package, which is NumPy package. And these type of things are called import signatures. And this is the standard import signature for NumPy, import NumPy as np. There's also other ones such as pandas and Matplotlib that we will use today, and Seaborn, also another plotting package. You can also import it other ways, but it will be frowned upon. And how do we use these packages after we import this? We can look up documentations online. So Google is always your best friend. If you type in NumPy, you can see NumPy here. The first one is the documentation. And you can go to this documentation tab to look at how to get started in using that. Usually very overwhelming. So that's why we're doing instructions to help you ease in using that. Okay, any questions on importing packages or downloading package? Okay, NumPy basics. So we first import NumPy, and please answer this participation survey on your confidence level on NumPy. See who has used it before or not. All right. A majority of people says least familiar. How many? 30. Okay. So most of people are not familiar with NumPy. So I will go through this step by step. So NumPy is very similar to Python list, but the only thing that's different is that it's using the same data type. So remember, in list, we can have a variety of types. For example, integer, float, boolean, strings, and maybe another list too. This is a list. But if you do a NumPy array of this, it will give you an error because it requires that you have the same data type. So what we need is that you have to have everything be within the same data type. For example, here I have an integer, so the other ones must also be integers. To manually define an array, an empty array will be just np.array, and then enclosing it with brackets. that's an empty array. And to define a manual array, you can just list out the things of the same data type within that bracket. You can also define multi-dimensional array. So here's an one-dimensional one. You can also define a two-dimensional one. You can think it as a matrix. So here is like a matrix of a 3x3 matrix. Any questions? So this is how you manually define an array. Sometimes you want to fill the array with things that you don't want to manually define. So that's where NumPy functions come in. For example, NumPy zeros will fill all these cells with 0. And if you don't know how to use this, you can copy and paste into Google, and it will pop up the documentation and teaches you how to use it with examples. Or you can also type a question mark, and it will print out the documentation string of how to use it if you're an advanced user. So here, NumPy zeros 1 means that it assumes you want an 1D array with length of 1. If you type 2, 1D array with length of 2, etc. But if you type in a tuple like this, it will give you a dimension of 2x3 matrix. So 2 is the row, 2 rows, and 3 columns. You can also define multi-dimensional array. Here is 3-dimensional. So here is 2 rows, 3 columns, and 2 of those matrix. This looks like this. And it will fill with zeros. You can also change the syntax to fill with ones. Similarly, 1D array with length 3, a 2D array that's 2x3. 2 columns, 2 rows, 3 columns, and then a 3D array. Any questions on creating arrays? You can get attributes from your arrays. So for example, here I created an array using NumPy ones, filled with ones. And I can ask, what is the shape of the array? So my array dot shape. It gives the dimension that's 2 times 3 times 2. The property ndim is number of dimensions. If you print it out, it's 3 dimensions, so 1, 2, 3, 3 dimensions. And dtype is the data type. So here it's float 64. And the size is the number of elements, total number of elements within. So if we count it up, it's 12. But interestingly, if you use the length command, so length of your array, it's 2. The reason is that it's looking at the outermost one. So it's looking at here, here's 1 list, and here's 2 lists. So the length is 2. But the size is 12 because it has 12 individual elements. Any questions on array properties? Array indexing and slicing will allow you to access elements in the array. So here I have defined a 4x3 array. The first way to think is to think it as a nested list. So I have here 1, 2, 3, 4 lists within there. So if you do indexing of the 0th element, that will return the 0th list. The first list returns in Python the first list. And if you want the first element, you want to go to the first list and then index the first element from that. And similarly, this is slicing. If we have nothing at each end of the colon, we have everything. If we have something on the left, it is from the first Python index to the end. So this is from the first list to the end. So last 3. Then here it's ending, starting at 0 and ending but not including 2. So starting at 0, ending but not including 2. So this is 0, 1, 2, not including 2, so it should be the first 2 lists. Okay. The other way to think it as is to think it as a matrix or multi-dimensional array. So you can ask what is at the 0th row and the second column in Python language. To us, it's row 1, column 3. So if we look at my array, let's print it out. Okay, I haven't defined it. it should be row 1, item 3. So it should be 3. So this is, in Python terms, third index, first index. So it should be row 4, 1, 0, 1, 2, 3. And then column 2, 0, 1, 2. And this is 1, so it should be 9. You can also select everything without any numbers. And this is from selecting from the first to the end. First index in Python to the end. This is selecting everything from the start to the second, but not including the second row. The first one will be the row, and the second one will be the column with the same logic. And you can do them at the same time. Any questions on slicing and indexing? Okay, so let's go to this problem and try this out. What is the output of the following code? You have an array that's 0, 1, 3, 35, 2. If you print this, what is the result? Okay, most people said it's the list 0, 1, 3. And that's correct, because we're viewing it as a list, and we're looking at the 0th list. That's 0, 1, 3. Okay, array operations. So if we define two arrays, we can manipulate them element-wise. Some element-wise operation would be addition, just plus them. So for each element, 1 plus 3, 2 plus 2, 3 plus 10. We can also do it with subtraction, multiplication, and division. And note that it's given us a warning that infinity is being raised because we're dividing by 0, because array 2 has an element that's 0. So we should be expecting that at that position we're having an infinity. So that's expected. Can also do comparison. Comparing an array with a number will give Boolean for all the elements. Comparisons for lesser or equal to, not equal to, and are two arrays equal to each other. So element-wise comparisons. Any questions? Okay, so that's the basics for arrays. NumPy also, because it's a scientific computing package, it also has a lot of mathematical functions and constants. For example, you can find the natural number as numpy.e, numpy.pi, and numpy.infinity, and numpy.nan is not a number. Okay, and something interesting would be if you, all right, let's show the functions. The functions, for example, we have powers. So this is 2 to the power of 3, 10 to the power of 3. The power is used as 2 star signs. We have 1e3. E means 10 raised to. So this should be 10 to the 3, so 1,000. And this is raised to the power of. You can also raise it to the power of non-integers. These two are equivalent syntax, but I would prefer this because it's easier to read. You can also raise it to a fraction that's below 1. For example, 0.5, that's the square root. And you can equivalently use the square root expression in NumPy. So numpy.sqrt, that's square root. Look at this poll question. What is 1e minus 10 in mathematics? Okay. Huh. Okay. And the answer should be 10 to the negative 10th. So don't be confused by the 1e. 1e means 10 raised to. Okay. Questions? Exponents and logarithms. So exponents, you can, so e raised to the something, there's a NumPy function called numpy.exp, that's exponent. So raised to the 0, 1, and 2. And something important to note for logarithm is that it's not intuitive in NumPy. If you want to use the natural logarithm, it's np.log. It's the natural logarithm. If you want log base 10, it's log 10. Log base 2 is log 2. So log base n is this syntax. Okay, so if we try it out, the first one is the natural log function. So we should expect that if we take the natural log of e, it should return 1. The second one is log base 10. And the third one, log base 2. So always remember, if it's numpy.log, it's not log base 10. It's natural log. Could appear on the test. And if you want a log base n for any arbitrary n, you can use this syntax. So for here, if we have log base 3, we should expect log base 3 of 3 be equal to 1. And that's what it returns. And let's try this poll question. So what's code of np.log1 in mathematics? Okay, natural log of 1, that's correct. So be aware of the weird syntax here. Trigonometric functions, we have sines, numpy.sine, cosine functions, numpy.cosine, and tangent functions, np.tangent. Some important things to note that we know that analytically sine of pi is equal to 0, but it's giving this gibberish. Why is that? It's because from last lab we are saying that computers are discrete machines. So this is basically giving 1 times 10 to the negative 16. So that's close to the floating point error. So basically 0. And this as well. So negative very small number approaching 0. So that's correct. And for tangent functions, we see that here's a 10 to the 1 times 10 to the 16th. That's basically saying that this blows up to almost infinity, which is expected. Okay, any questions on floating point errors on these? Okay. Inverse sine functions. You can see it as an arcsine function or also sine to the negative 1. That's an inverse sine function. We also have inverse cosine and tangent function as arc cosine, arc tangent. Sometimes because all these arguments are in radians, if you feed it degrees, it will give you an unexpected result. So if your input is a degree, you want to convert it to radians. So to convert it, you can use the degree to radian function, so dig to rad. Or conversely, you can convert from radians to degrees. This practice problem, what is sine of 0 raised to the negative 1? Okay, a split. We have a split between arcsine and sine of 0 raised to negative 1. So we have to make the distinction between these two. Mathematically too. So if you have sine of negative 1, this is an inverse sine function. So this is equivalent to arcsine. But if you have sine of something, the whole thing raised to negative 1, then you must do it step by step. So first, sine of 0 is 0. 0 to the negative 1 should also be 0. So in this question, looking at the order of operations, it's having sine inside and the exponent outside. So that should be the third option. You don't need to correct it. It's based on completion. Okay. And let's go. Almost there, almost there. The boring stuffs are gone. Okay. Range generating function. These are very useful for looping. So if you want to loop or plotting things, these will be very handy. So a range means a linear range. So this basically works very similar to Python's built-in range function. So if you just give it one argument, 10, it's basically the one that's stopping but not including. So it starts automatically at 0, and it stops and not include 10 on a step of 1. You can change it up as starting at 2, ending but not including 11 at a step 2. So that gives 2, 4, 6, 8, 10. When it wants to step to 12, it says, oh, it's bigger than 11, so it stops. You can also do it reverse in a smaller step. So you start at 11, ending but not including 2, with a negative step size of -2. So it counts backwards. 11, 9, 7, 5, 3. And it wants to count to 1, but the end should be 2. Okay? That's what we have already know. But this new function will be very useful. Linspace. It says linear spacing. So the syntax is that the first one is that you're starting and including this number. So starting and including 0, ending and including 1,000. So this is different from range function. In range function, this is ending but not including. But for linspace, it's ending and including. And with a total of 11 points. So if you have linspace of 0 to 1,000 with 11 points, that's 0, 100, 200, etc. to 1,000. And you can also do it reverse. So starting and including 1, ending and including 1, with a total of number of points of 21 points. So these two are used in different situations. A range is used when you know the step size, and linspace is when you know the ending points, because you want to include both endpoints. Okay, let's look at these polls about range functions. What range generating function should be used if we want to specify a step size? If we have a step size, we use a range. That's correct. And if we have the left and the right boundary, we just use linspace and then supply the number of points we want. Nice. Okay. All the boring stuff are gone. Any questions? Okay, good. NumPy, the exciting part, plotting. So let's look at your confidence level in plotting. Okay, quite a spread. There are no expert visualization people. It's good to know. Okay, great. Thank you for participation. And from now on, I won't be just lecturing and lecturing. So boring, right? So what I will do is to do some live coding with the guided examples. So plot the following analytic function in a figure. F equals to sine of x in a domain that's specified. So unlike a graphing calculator, if, for example, using Desmos, you just type sine of x. Oh, wow, continuous function, so nice. But we have to keep in mind that computers are discrete machines. So we have to specify to them, like giving lectures to high schoolers, that we want to specify individual points. So what we actually need to supply is individual x and y coordinates. So for sine, it's a 0, 0. If it's pi, it should be what? Also 0, right? So individual points, connecting individual points. So what we do is to first define x within that domain. So define x equals to, so here, what range generating function should we use? We have a left boundary, we have a right boundary. Linspace. So we have NumPy dot linspace, basically using the linspace function from NumPy. So left boundary is -2 times NumPy dot pi. So remember, don't just write 2pi, because you have to use a Python syntax. So ending at 2 times NumPy dot pi with some number of spacing. Let's try 10, plotting 10 points. And then y should be equal to the sine function, right? So NumPy dot sine of x. So let's print it. So in Jupyter Notebook cells, if you don't type print, it will automatically print the last argument, so x. So we see 10 points, and y also 10 points. So what we do here is to just plt. So this is the importing signature for MATLAB. So import matplotlib.pyplot as plt. So plt stands for plot. So this is the package that we're using. So this is basically saying, from that package, I want to use the function plot. And what are we plotting? X and y. And this will give us the plot. Does it look like sine function? It's a little jagged, right? Why is that? It's because of the discreteness of computer. We're only supplying it 10 points. But what if we supply more points, say 50 points? So if we supply 50 points, we have 50x, 50y, and if we plot it, we're supposed to get a smoother one because we're making the spacing closer. So again, 10, very jagged. If we increase to 20, should be smoother. Further increase to 30, smoother. And because nowadays computing powers are very cheap, lots of points, very continuous. Okay, but early days people have to do it very small because it's expensive to compute. But for us, we can do a lot more. Okay, any questions on this example problem? You should also have those code with comments in line. Okay. Second guided question. Plot the analytic expression with these additional constraints. So first we have this function. Last time we didn't define a function because it's built in, it's sine function. But this time it's a polynomial function. So what we can do is to define a lambda function named f. Lambda and the variable name, let's say x, with x to the cube plus x squared minus 2 times x minus 2. Okay, this is the function we define. In the domain from x equals 2, we already know the left and right boundary, so lin space. Left bound is minus 3, right bound is 3. How many points? We already know we want larger number of points, so let's do 1,000, arbitrary. And then y will be equal to the function evaluated at x. So plugging this x in, it will automatically compute how many points we have. So let's print it out. So f is a function, x is 1,000 points, so busy, and then y should also be 1,000 points. Okay, and we can plot it with PLT. So from that package, we use the plotting function x comma y. So this is our polynomial function. And there are some additional constraints. We want to set the line width to 5. So within the same line, we can add some attributes to make it more beautiful. So line width will be just plotting line width is equal to an integer or a float, say 5. So the line width now will be 5, very thick. Line style changed to dashed line. So we can say, is it line style? I think ls. Line style equals to dashed line. And what is dashed line in Matplotlib? I don't know, right? So we can just say plt.plot. Google help us all. Okay, looking at what's dashed line. Okay, line style equals to dashed. Okay, we can just put that in, dash. Okay, it's given an error. Oh, dashed, thank you. Dash ed. And you can also look at other syntax. It's not limited to this. So if you look at the syntax, this dash line, you can also do it like minus minus. So let's try that out too. So if you supply minus minus, it should also give you a dash line. You can also try like dot dash or dash dot, like this. There are a lot of different syntax if you want to look it up. Okay, line color to black. So that syntax is color equal to black. And there are a lot of other like things that you can do. You can search it up. For example, black can be represented by quotation mark K. Same thing. Okay. Set the x limit to minus 3, 3. So currently it's a little beyond. So if you want to make it prettier, the command will be plt dot x limit. So the first argument is the left bound, minus 3. Second one is the right bound, 3. If we run it, it's from minus 3 to 3. And similarly, we want to set y limits. And we can copy and paste this code. So on my end, I'm doing shift option down. So it copies it for me. Or if it doesn't work for you, you can copy and paste. So change it up to y limit from minus 5 to 25. Okay, now it's from minus whatever to 30. So we set it to 25. label the y and x and y axis. So plt x label is the syntax. And x label, we can label it as x. Okay, here shows up in x. And similarly, want to change it with y label. So y label shows up. Label the figure with the title and the function name. So the syntax is plt.title. And then in the title, we want the function name. So here we can use LaTeX syntax. If you're not familiar, it's okay. But the LaTeX syntax is x to the third plus x to the second minus 2x minus 2. And it plots this LaTeX syntax here as a title. Any questions? And this is the simple way of doing it, beginner's plotting method. But sometimes we want to plot more advanced method, so we can expand the variety of plots we can do. So with the same x and y, there's another plotting method which I will be using for the rest of the lab and this course. And the syntax is a little bit complicated, but you will remember after you plotting those a lot or copy and paste a lot. So the syntax is plt.subplots. So this gives you an empty plot. And then we can assign figure, so this whole thing is the figure and axes to it. So it returns a figure and an axis. I'm assigning it to it. And to plot within this subplot, we need to use x. So x is standing for the axis. From the axis, we're plotting x and y. So same thing. And then basically, all the similar command can be used. So I'm just copy and pasting here. So copy and paste, and changing all the plt to x. Right, and run it. And we see that there's an error. This is because there's a slight syntax difference between the beginner method and the advanced method. In the advanced method, we're treating this figure as an axis. And from those axes, we're changing the properties or attribute of the axis. So what we want to do is to change it to set x limit, set y limit, okay? And then set x label, set y label, and then set title. And this generates the same plot as before. Any questions on this more advanced plotting method? So this line is the hardest one, and everything else is just using x. And then remember the set command. Okay? There's more annotated version down below. Now it goes without saying, you must label your axis and figure appropriately with x and y labels. That counts for all your chemical engineering homeworks. If you don't label it, points are gone. Okay, guided example 3. So plotting functions, but now we're plotting 3 functions in one figure and making some additional adjustments. So this time we have 3 functions, but we're sharing the x. So x initially should be already have left and right, so we have NP link space from -2 times pi to 2 times pi. In best practice, when you're coding, please ensure there's a space between operators like this. Do not cramp it up. So this is like the standard way for coding. Okay, so we have x. And then we are evaluating these functions, and these are built-in NumPy functions. So what we can do is to say function of sine. So y of sine is equal to the NumPy sine function evaluated at x. So this will give us how many points? I think some number of points, because we didn't specify, so it defaulted. Let's do 1,000 points. So now it's 1,000 points. And we can do similar things with cosine and tangent. So y of cosine, we use cosine function, and y of tangent, we use tangent function. Okay, these are 3 y's. And so now using the advanced version, so fig x equals to plt dot subplots, Okay, we have the axis, and for each axis, we want to plot the x and y. And here, y should be corresponding to sine. Okay, here's a sine function. And then with another line of command, we plot cosine. And with another line of command, we plot tangent. Okay? And why is it showing up like this? This is because when we're plotting tangent at, see, this is pi divided by 2, it blows up to infinity, right? It's expected. Let's see, sine, cosine of x, and then tangent of x. It blows up to infinity. It's expected. But this is not so informative, is it? So what we want to do is to change the range. So the domain should be this, and the range is here, specified. So change the x limit. So axes, set the x limit to minus 2 pi to 2 pi. Just copy and pasting. Don't want to type. Okay, now it's minus 2 pi to pi. And then the range, it's set y limit from minus 1.5 to 1.5. Minus 1.5 to 1.5. So now this is more informative. But there's no legend. I don't know which function is which. So what we need to do is to label each line in a legend. And to do that, we use, within the plotting command, we say label is equal to the thing that you want to label. For example, here I have a sine function. Similarly, we have labeling for cosine function and labeling for tangent function. If you run it, there's no legend. Why is that? It's because you only labeled each one, but did not give it a legend. So what you need to do is for an extra command, say x legend, and it will show up in legend with the labeling. The reverse is true. If you only give it legend but not the labeling, it will show up an empty legend here and telling you, what are you doing? You're not giving me labels. Okay? Any questions on labeling? All right. Make the sine function line red. Okay, so that's just the color command to red. Okay, sine function is now red. Make the cosine function a dashed line. So that's the line style. So you can type line style or ls for short. And then dash dash. That's a dash line. Make tangent function transparent with an alpha of 0.5. So if you want plot to be transparent, that's we're using alpha function, alpha property, set it to 0.5. And now it's like a little bit transparent. So alpha of 1 is no transparency. Alpha of 0 is totally transparent, so you can't see it. So 0.01, very transparent. Okay, 0.5. Any questions? All right, I think now it's your time. Okay, before that, there's a secret sauce for better visualization within Jupyter Notebook. So if you're doing this for homework or a report, I would recommend adding this. So if you run this, and then rerun the code that you previously run, you'll see that the plot becomes much more crisper. It's because that this is giving you a higher resolution. All right, so now it's practice problem. Let's let you code the problem. Let's do 5 to 10 minutes, and I'll check in with you. Please raise your hand for any questions. Reducing code. It's for later. We'll see in the slides. We want adjacent to each other.
Right.
The first one is very hard. The second one is easy.
Right, so how would I do it for the first one? Because I think it's required that I do this one as well. You plot 4 functions for the first beginner's plotting method.
Is it within the same figure or separate?
Same thing.
In the same figure, then you just do.
Just to be.
Yeah, both can be. So what's the problem with that? You just do
Do I do it 4 times or?
for one for each path.
Oh, so I just do this 4 times.
Yes.
Alright, cool. Thank you.
I had a question with last week's lab. I am not good at making for loops and then calling them into a function. That is not. So I've created, I think it was using Newton's, it was Newton's method. I created, I've got the formula ready to go. I just don't know how I'm supposed to get a for loop to call for each of the
Initial guesses.
yeah. I don't know if we were just supposed to create, that should be a list, right?
Yeah, so now you're turning it into a tuple, which is fine. Works either way.
Did I have a list to begin with?
Yes, this is
Okay.
a list. And then, so this for loop is the Newton's method algorithm.
Yep.
And in a separate cell, you want to loop through all these different guesses.
I see.
So for I in range of this, or for x, for guess in x0, either way, how do you choose? And then the syntax is like this.
Oh yeah.
And then because you want to call this one, and you want yeah, you already have it. So f is here, f is here, column is here, max iteration is there. And your guess x0 is just guess. Yeah. Because this is a function, it returns something but does not print anything.
I see.
If you want to display the result, you need a print statement. So here we define it as, so you need something to plug in here. So you need to define max iter.
How many times do we want max iter? Let's say 10,000.
Please raise your hand if you're done.
Why is it not liking?
Xn, is Xn previously defined?
Look at it.
So this is,
That's for. Where's Newton's method? Yeah, I don't think xn is previously defined.
looks pretty good.
It looks pretty consistent, yeah.
Is negative one almost
Like with 0 iterations, I was.
Yeah.
But should that be is that correct or is that?
Because this function we have done before, right? So you can double check if minus one is, because we've done as a practice.
-1 plus 1. It looks right.
Yeah.
There's -1, that's 1, they cancel each other out, that's +2, that's -2. That sounds about right.
Okay.
Thank you.
special one that says like import. You can just type it into your main if you want. Oh no, you wanna, so for that one, it's gonna be like import NumPy as NP, because right now it doesn't know what NP is, like it's gonna be this one. Yeah, this one. Yeah. Now it knows what NP is, and same for Matplotlib.
Yeah.
So there's no appeal to this. Yeah, I think once you like went through the manual one, you're not gonna have it. Yeah, then you should try that. Okay, yeah. So maybe specify an X variable, or you can, if you're looking for like this X, you just have to run it.
Run this.
I think they're all connected, but I don't know what your specific bounds are. So you can just add it in.
Yes.
Oh, you're using, so,
Yes, but it's wrong.
yeah. So, like the way you're specifying the variables, it looks like xlim, like your data that you're trying to like, apply the function to. So if you put xlim, like
Xlim instead of X.
yeah, that might work.
This one?
And yeah, so log 10 is not correct syntax. You want to do, so log is like a NumPy function. So you're going to have to use
NP.
yeah,
NP dot log.
NP dot, but then log base, actually see if that runs. Maybe they have a shorthand for it.
Oh shit, not yet. Oh no. My log? Is this supposed to be, this is just regular one base?
Oh yeah, so log 10 isn't going to work. So when you do log is going to do that. Because when you type in log, it's just an option.
That's what I put it. This one?
It says invalid value encountered in log 10.
How do you have it as?
So if you want to look at like log 10. So your exponential log weights actually do that. Or you just want That's because you're putting negative numbers in there. No, you can't do negative log. So it's so you can define a new length space from 0 to 2. Or yeah, but 0 is also going to throw an error. So you can try that. Yeah, the range of the entire. So the domains of the range. So maybe try to find new. So if you're just calculating stuff, you do X amount of your own, and then later when you then Because your only range has to be from -2 to 2.
Yeah.
Where for the block space,
Yeah.
that's perfect.
Do any backside or what's the backside?
That would work so crap. Have the error.
I just got rid of the backslash.
And then, yeah, it's just the same arrow.
Yeah, I mean, it doesn't know.
Okay, so it's okay.
I think it should be. I don't know if I don't know how the grading works.
Yeah.
I think it should be better.
Okay.
Please, there you go. I think I opened the thing for
This thing again.
unless I misunderstood an annihilation of this.
But it's probably good.
It's not supposed to look like this.
Maybe
I don't know if that looks like that. So, but you might just check. You might. It looks fine. For T goes to 0 to 20. Yeah.
I did not expect it. I don't think,
Isn't this supposed to be, this is logic?
Yeah, it's
Because
fine.
natural logic.
Yeah.
Because, yeah, you're
it's like automatic.
No, it's not. No. That is not.
I went ahead a little bit, but that does not look.
Okay, yeah, I'll follow up. Yeah, but I mean,
Oh.
if you're plotting it, okay, fine. Yeah, thanks.
I have a question. Alright, so in this problem, this is log-based 10, right? And that's how you would
That might be.
Doesn't look like words. Or is it my problem? Did I specify?
Just set the aspect ratio of the x and y values to y. I have my aspect.
Might be my problem.
Oh, that's why.
Okay.
Yeah, you have to do.
The fourth function.
Oh, for that, it's just yeah. And then comma LW equals 2. And then, yeah, and then same one for
This one?
yeah.
Just confirming your graph might have mixed up.
Yeah, it might be my problem.
Did you get this as well?
Yeah, exactly.
Okay.
Okay.
Yeah, Python's not my forte, but it was pretty good on my end.
It's funny it's on the same
I don't know.
I deleted it.
I did.
I don't think we got it. I don't know what it is. I know,
Okay, so X-Men, X, X, problem. We have the same thing, right? Because labels don't really matter.
Okay, are we ready to move on to more plotting? More fun plotting? Okay, keep going. Okay, so plotting parametric functions. So we just covered how to plot a regular easy function. Well, but what about parametric functions that we might see? So here we're plotting a polar defined parametric function in Cartesian coordinates with some defined domain. And then there's a conversion between polar coordinates to Cartesian coordinates. So here we want to do is to first write down the equation. So r is equal to theta plus 1 to the negative 1. That's basically 1 divided by that. Okay. And then x is equal to r times cosine theta, and y is equal to r times sine of say theta. But note that theta isn't defined, so let's define it. So theta should be between 0 and 20 pi. So np, no one left and right, so lin space 0, 20 times np dot pi. Let's do lots of points. Okay, let's run it. So we have x and y's. So see if we can plot it. So the syntax is fig x is equal to plt dot subplots. We have axes, so axes dot plot x and y. So this gives a spiral, but it looks squished. The reason is that the aspect ratio is not the same. It's accommodating to this particular size of box. So what we want to do is to set the aspect ratio such that the x and y, the aspect ratio is 1. To do that, we can use x dot set aspect. If you don't know the functions, you can press tab on your computer, and it'll give you all the functions here. So we are looking for aspect of 1. So now it looks better. And then doing other stuff, plot in the domain. So that's set x limit of minus 0.5, 1. Set y limit to minus 5 to 0.5. Okay. Plot black and dashed vertical and horizontal line that represents y equals to 0 and x equals to 0 and y equals to pi. So that command can be done with x dot xh line, that's horizontal line, which is y is equal to. So we want y equal to pi, np dot pi. Okay, it's not. Oh, maybe it's 0, it should be 0. So I'll change this problem to 0. Typo. To 0, and then we find that the color isn't right. We want a black and dashed line, so we can change it with color is equal to k, and line style is dash dash. And then for fun, we can change the line width to 1, 2. And similarly, we do this for vertical line, which is used with xv line as vertical. And now we have horizontal and vertical lines. Questions? Okay. And you can practice with this problem, but please note, there's a problem with the problem. So you need a parentheses after the sign, I think. So do a parentheses here, like this. So you're multiplying everything. And hopefully that will give you a butterfly. Thanks for pointing it out. That's why it's crazy today.
Oh, there we go. the y equals pi, if the line is not.
Right. I think it's a copy and pasting question.
Okay.
So I have so many questions, I copy and paste them.
Yeah, I
So
just didn't know if
zero,
I didn't know if I was doing something wrong. Okay.
zero, my intention was zero, so.
Okay. Thank you.
And then it doesn't find it.
The reason, do you identify the reason?
It's because the bottom wants to.
That's
So
worth it.
when the definition defines a negative
Oh, yeah.
and a negative.
Yeah. Oh,
That's a lead. You can look at that.
yeah.
What do you got?
Like I've checked my answer. Check. Did I not do 4 times theta? Or 4 times it? What?
Oh, you need a parentheses.
What happens?
You need a parentheses.
Because that one got messed up.
Yeah.
Yeah. They had to add an extra parentheses. And then this was that one. Because it's
Wait, I don't think so.
Oh, you put
Because I put
exponent.
EXP and this put E.
Yeah, that one's right.
Did it run?
What about the bottom?
I literally copied
Yeah,
it.
the bottom part, I didn't change anything.
Yeah.
There we go.
It was just the
Yeah,
parentheses
yeah.
there.
It was from the original one.
Yeah,
It was messed up.
they forgot to add parentheses for our copies,
Oh.
and they added it later.
Okay. So what's my goal?
No.
All right, let's do another easy example. And this time, we will have some chemical engineering background. Plotting streamlines. So if you take a fluid mechanics class, which is in transport, you might have encounter streamlines. For your system of interest, chemical engineers found streamlines are defined by a parametric function, x of t and y of t. And then they wanted us to plot all of these streamlines. What do we do? So we first define the functions. So f equals to t plus 1 plus minus 0.5 multiplied by natural log. So natural log in NumPy is np dot log. And then multiply by t to t squared plus c squared. Y is equal to c plus arg. So the argument, what is this? This is an imaginary thing. So if we don't know things, we can go for Google. So arg complex number. So it's basically taking the complex number and finding its angle. That's what arg is doing. And if we add this to Python to see what we can do, there's a function called numpy.angle that gives us the angle for the complex argument. And for that, we can use that. So np.angle of t plus c times I, imaginary number. Imaginary number in NumPy is j, so 1j. If you print that, that's an imaginary number. So this is x and y. And then we have to define the parameter t from -2 to 2. np dot linspace -10 to 2. Plot 10 streamlines defined by 10 equidistant c. So that gives us the constant c is equal to np linspace 0 to pi with 10 equidistant ones. Okay, then let's see if we have x and y. Name error, c is undefined. this should be C. Okay, C should be an integer or a number. So we're looping through C, so we shouldn't just feed in the whole list. So currently C is a list. So I'll change it to C list. So what we should do is to write a for loop. So for C in C list. So for element C in C list, I have this. So I can print Y. Oh, C. Here's the C. Now I have different Y's. And then I want to plot them. To plot them, we first have fig x plt.subplots. Okay, we have that axis here. So for each loop, within the loop, we want to plot within the axis, x and y. Oh wow, okay. That's strange. Oh, this should be C. Okay, this is the streamline. And then let's set other things. So make the streamline blue. So color is equal to blue. Plot in the domain. So x set x limit -5 to 5. And then y domain, y range should be 0 to 10. Okay. And plot the horizontal and vertical axis. X dot xh line. Horizontal is pi. And then vertical is 0. And then let's set the color to be black. And then the line style as dashed. V line. Okay. I think something's wrong. I mistyped something. C plus argument T plus C times J. Okay. Now this is the streamline. And then we only plotted the top 10. We wanted to plot another 5 using the same code. So I'm just going to copy this and then paste it. And the linspace, so here the C list is different. So here the C list is from 0 to pi divided by 10 in 5 equidistant points. And this is the final streamline. And we can also increase the granularity to make it more continuous. example that's not similar to what you have done. So please pay attention. So this is plotting simple function in multiple subplots. So what we have done is to plot multiple functions in one plot. But here we're doing it multiple subplots. So the example here is plotting analytic expression and plotting them in separate subplots that is arranged in 1 times 4 rectangle. So basically we have 1 row, 4 columns. What we want to do, what we can do is to have x. So first define the x. So NP lin space minus 2, also higher, 2 times pi. And then f of sine, so y of sine is equal to np dot sine of x. Do the same with the cosine and tangent. And now we should have our thing. Let's do it with a lot of points. Okay, 1,000 points. Cool. So usually what we plot is fig x is equal to plt dot subplot. And then we can plot on each axis. Okay, subplots, not subplot. Okay, this is the usual way. But here's the trick. If you want to have multiple subplots and arrange in a rectangular thing, you can put arguments here. So put arguments 1, 4, that gives 1 row, 4 columns. So like this. And let's look at what fig and x are. So fig is a figure, and the x is actually a list of axes. So what I should have called it is axes. And here we have 4 axes. So x is a list. So that if you look at the type of the ax, it is a list. And within each of the axes, we can plot it. So here, x of 0, the 0th axis is here. We can plot it. Okay, this is axis here. And then the first axis, we plot the cosine function. And the second one, we plot the tangent function. And what's the fourth one? Fourth one we plot in one figure. So all 3 of them in one figure. So copy and paste, change this to Python index 3. So all of them are in one figure. Yep. And it's looking weird because tangent is going to infinity. So what we want to do is to change the domain and range for all of them. So what we can do is for all the axes, we change the limit set x lim to minus 2 pi to 2 pi, copy and pasting. And then change also y to minus 1.5 to 1.5. Okay, we have changed the first one. But if we want to loop it through everything, that will be tedious. So what we can do is to, for I in range of 4, all those 4 plots, change it to I, since these are shared commands between all of the subplots. So now this looks better. But now this looks very squished. So what we want to do is to set the figure size so that it matches the dimension. So to do that, we use in the subplot command, use fig size for figure size, and make it 12 inch, the unit is inch, by 4 inch. And now it's like a more spread out. And make each box aspect ratio as 1. So all of them share the same one, so we can do it within the loop. So set box aspect. Here is not the XY ratio, it's the box aspect, so the box of here. So after this command, these should all be squares. Okay, like this. And then usually I will add a magic command that will make this more beautiful. So plt.tightLayout, this function, it will give them more space between. And that is the practice problem for this. And of course, you want to label the x and y. So label everything's set x label as x and set y label as y. And you should also do the legend thing, which I will not show here because you know how to do that already. Okay, and another example. So we have the same thing, same functions, but now we want to arrange it in 2 times 2 square. So all of these x and y thing we can copy and paste. But we need to change the command for plotting. So the x and y thing keeps. And we want to change it to 2 by 2. So when we do this, we change it to 2 times 2. And let's see what fig and x are. So figure is still one figure, but axis now is a 2 by 2 axis. So in order to access each one, we need to do 0, 0 index, 0, 1, 1, 0, and 1, 1. And so let's do that. So we have 2 times 2 and arrange into figure of 7 inches times 5 inches. So 7, 5. And for each of these, we need to change to 0, 0. The first one is 0, 1. The second one is 1, 0. The fourth one is 1, 1. And here we also need to change. So we can change from I we can define it as the row and define j as the column. So I and j. And now we have it in a 2 by 2 layout. Okay, and you can practice it with your practice problem with an ordinary differential equations solution. Before that, I want to also introduce you to some other secret sauce. So if you run this type of command, which you can change very granularly, the font size, font family, the line width, etc., you can get a much more professional plot too, like this. So this might be useful for your future reports, homeworks, or just for fun. Okay, that's all the practice guided problems. And before you go, please submit also your participation survey in Google Forms. And the completion of this lab will contain 11 Poll Everywhere survey, 1 Google Form survey, and 6 practice problems. And practice problems are uploaded on Facebook. And you're free to go, or you have 7 minutes of more.
I'm just trying to see, is mine,
Tuesday,
It's called the bloomer. It's because I have mine. Yeah, it's because you changed the color of both.
oh yeah, because I have two.
Yeah. No, I don't have to. I have just one.
after you have like f, how would you go about like solving this differential equation in terms like the left and the x? Do you just because f is a constant. Yeah.
So when I learned this, I did not do the derivation. So I did not do this type of derivation. So I'm not extremely familiar. So what I have is, oh, let me stop
Because
recording.
we're trying to like